Today we are going to talk about lecture number 6, multi-link structure of robots and linear algebra. The emphasis is on this linear algebra here. And that's part 1. We will divide the lecture into 2 parts. Okay, anyway. So why linear algebra? Well, let's go back to the posture of a robot, because we used figures as a posture. It's easy for human beings to understand. But how about a set of angles? The robot posture, as I discussed before, will be determined by the joint angles. If you decide the joint angles of every joint you have on your robot, then you have one posture. So that's set. If, for example, here it's only 4 angles here. Okay, how about a vector of angles? So vector, there is a thing called a vector in mathematics, which looks like this one here, is a set of elements. That sounds like exactly what we want, right? We have a set of vectors and put them together, and that is a posture. So what we do is we use a vector of angles theta as the posture. So that is going to be our posture. Aha, that's very convenient. And when we look at the vectors, there are lots of things you can do with the vectors. And there's another thing called the matrix. The matrix is also very convenient, and it can be used together with vectors. Therefore, we will discuss both vectors and mathematics. Of course, from robotics point of view, the vector of angles is a posture, so therefore that is super handy. So that's what we want to use from robotics side. But from a mathematical point of view, there is a lot of relationships between vectors and matrices. So therefore, what's going to happen is that it is very effective if we learn both of them at the same time, like using this matrix and vectors. And the area of mathematics dealing the matrices and vectors is called the linear algebra. Linear algebra. So that's what we are going to talk about for a while, this lecture and next lecture. But, well, linear algebra is such a deep subject that 2 lectures is not enough. So what we can do here is the introduction of linear algebra. You will have another lecture which is devoted entirely to linear algebra later. Okay. So let's go back to an example of Mach 5 here by Dr. Furuta. He is my boss right now, and he used to be my student. But anyway, number of joints of Mach 5 is 22. So that means 22 things has to be put together. So we will have a vector of 22 of them together. And that we use the word dimension. So this is 22-dimensional vector. Or you can say this vector is of 22 dimension. Okay? So how about a motion? If you have just a number, it's just a figure, right? If it is not moving, it is just a figure. And robot has to move. Then what's going to happen is this. A vector of time-varying angles, namely functions of time. If you put together 22 functions of time, that is going to be the motion of your robot. Once again, it is very, very useful, isn't it? And very handy. You just put those functions here, and that is going to be the motion of the entire body. Okay. So when we design a motion for a robot, what we have to do is to determine those functions, time-varying vector. Well, we use this word time-varying vector for that. In robotics, we use not only time-varying vectors, but also derivative vectors. the derivative vectors which contains the derivative of those functions. Well, you saw that already in Dr. Yamato's equation. Let's take a look at that equation one more time. Well, EOM stands for the equation of motion. As I said, mathematicians are lazy, so we always abbreviate. Instead of equation of motion, we say EOM, COG, center of gravity, blah, 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 etc., etc. Motion of Mach 5, a part of it for working. Remember, this was only for the working, so 5 joints only, from hip down, that's it. And it looked like this one here. And there are lots of vectors, theta double dot, theta dot square, theta dot, theta, d. Notice that this one does not even have this one here, this part here. The reason for that is that because most of the time with the robotics, we use vectors, not just a single variable. So therefore, we don't use those special signs for the vectors. In other words, default is a vector. So every one of them is actually a vector. All right? And then matrices. As I said, vectors and matrices all together, we use them together. A, B, and C. Notice that those are capital. Large A, large B, large C's. We use that for matrices. Okay, this equation is too complicated, as I said. So therefore, what we do is to divide and conquer. So we look at simpler case, well, that's engineer's maximum 3, if you remember. Let's start from a simplest case of those matrices and so forth. Well, what do you think is the simplest case? You guessed 2-link manipulator? Well, even simpler than that. Linear simultaneous equation. Well, actually, that's a place where this linear algebra whole thing has started. So to understand something, it is a good idea to follow the history of that discipline. It started from linear simultaneous equation. The simplest one is like this one. Ax plus by is equal to e, cx plus dy is equal to f, where x and y are variables, and a, b, c, d, e, and f are parameters, constants. Okay. Okay for classroom here. Right, 2 by 2. But for our case, say for example, if you have 22 of them, 22 variables, 22 equations like this one here, well, that's dot, dot, dot notation here, and dot, dot, dot notations here. So therefore, this is an abbreviation. But write all equations without abbreviation? Well, if you remember that Dr. Yamato's equation takes 4 pages, right? You don't want to do this, okay? So what we do? Vectors and matrices, that's what we use. How? Okay, I'll show you. Okay, starting from this one here, right? And we write this one, we write this one into this form, and then to this one here. Okay, so instead of that equation, we have this equation here, where vectors, and a matrix here. Okay, so instead, when we rewrite those 2 equations into this one equation, we defined 2 vectors and a matrix here. Okay. Notice that I haven't defined, say for example, this looks like a multiplication of a vector and a matrix. Here is once again vector and matrix multiplication. I haven't defined that formally, but I'll do that in a minute. But if you can understand that instead of writing those, we do this and that by defining vectors and matrices. If you follow this flow, then you can understand the definitions of the multiplications easily. Okay? So what we do is we define vectors and matrices, and then we will talk about addition, subtraction, multiplication, and division. Those 4 operations, arithmetic operations. Well, remember when you learned in grade school, when you learned numbers, after that you have learned how to add, how to subtract, and how to multiply, and how to divide those numbers, right? So we do exactly the same thing with those matrices and vectors. Okay. However, because matrices and vectors are a little bit more complicated than regular numbers, so we have to do some preparation for that before talking the arithmetic operation. So with preparation for arithmetic number 1, so I have more than 1 page of this. Before going into the arithmetic, we look at the size. Yeah, the size of the vector matrices can change, right? Or you can put together only 2 of them over there, or many of them right here. You can put 2 and 2 here, but you can put many of them n rows and m columns or whatever. So the size of those, we should have a way of saying what the size is. So we decide that the size is, we say number of rows cross number of columns, and we say by. So like this one here is 2 by 1, this is 2 by 2, 2n by 1, and this is n by n, because this is n rows and m columns, n by m. Okay, so that's how we say the size of the matrices and vectors. So if you look at that, then you can tell that if you have only 1 column, that is a vector, right? So therefore, a vector is a single column matrices. So therefore, vectors and matrices are pretty much the same thing. That's why we are going to learn both of them at the same time. Okay, the next one here. This is once again because of the matrices and vectors. They have lots of elements. That's why we had to talk about this. A transpose of a matrix A T transpose. Switching rows and columns. That's easy to understand by looking at an example. Here, if you have A, this is 3 rows and 2 columns. This is 3 by 2. And you switch rows and columns. Then you get this. Instead of the first row, you have first column, second row, second column, third row, and third column. So this A transpose becomes 3. Instead, if A is 3 by 2, then A transpose becomes 2 by 3. Switching. Okay. Well, we do this quite often. Okay. How about some notations? You may have learned many different notations. Here we cite ones we use. Namely, in high school, depending on where you learn those vectors, you must have learned vectors or matrices before. And you may have used many different types of notations, how to write it. But this is what we use in this lecture. Matrices, a capital letter, A, B, C, D, etc., etc. Or if you're looking at the elements within matrices, within a matrix, then we use this one here, A, I, J, and M. And this one here, meaning that, actually I write this one down here. That's 1, I, N, and 1, J, M. That's what this I, J, and M means. So N by M is the size of the matrix, and the elements are A, I, J, where we call this Same here. I runs from 1 to n. I runs from 1 to n. J runs from 1 to m. That's what we call. Or you can write down this form, but interesting thing is that here, those are braces, but them are brackets. Okay. That's a notation we use in this class. How did you learn? Did you use those? Some of you may have used the braces for this form, but brackets is the one we use. Okay. Vectors, this notation here. If I enlarge that, it's this. Some people write this one here, but no, not this one here. Just only the upper side you have a vector. Or this same notation as a matrix here. Okay? How about inner products? We will talk about inner products. You may have learned inner product in high school. And that's probably some of you had this one here. And this, probably not this one here. Probably you never had. You may had a parenthesis kind of things, but we are not going to use that because we use that for something else. All right, summation. This is a capital sigma, Greek character. We use this capital sigma and write down k runs from 1 to m. Once again, k runs from 1 to m, ak. So this notation here is exactly the same as a1 plus a2 plus blah, 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 up to am. Runs from 1 to m, okay? So you got it? So once we have the notations and the sizes and transpose, etc., etc., the next thing we have to talk about is the equality. Well, two numbers are equal, obvious, trivial thing, right? 2 and 2 are equal to each other. But matrices and vectors, they are equal to each other if two conditions are satisfied. One of them is that the size. Sizes are the same, and all corresponding elements are equal to each other. Okay? And size needs to be the same, otherwise corresponding element doesn't exist. So size is the condition of two matrices or two vectors to be equal to each other. Okay. So Aij and m is equal to Bij pq if n is equal to p and m is equal to q, that's size. And Aij is equal to Bij for all ij, that's for same ij. Okay, that's what it is. All right. Now we are ready to talk about arithmetics. And simplest one is what? Addition? Not quite. Scalar multiplication is the first one we'll talk about. Elements are multiplied. What do you mean by that? Well, if you multiply a scalar, I don't know how to pronounce it. There are two pronunciations. But anyway, if you multiply something like a 2 or pi or e or whatever, 3.5 or whatever, to a vector, what's going to happen is that value will be multiplied to each and every element. How about matrix? And exactly the same thing. If you multiply a number to a matrix, each and every element of the matrix will be multiplied by that number here. Okay, that's easy. So now let's start talking about the addition, the simplest one. All right. Defined only for the same size matrices. Once again, when you're talking about equality, you have to have same size. And if you're talking about addition, you have to add two matrices, but they have to be exactly the same size. Why? Corresponding elements must exist. So the addition of these two matrices is defined to be addition of elements. That's the reason why corresponding elements has to exist. That's the reason why those two matrices has to be of the same size. Well, that's understandable, right? And here, I guess I'd like to mention one thing, which is the matrix addition here, that's a new thing, right? Is defined by the scalar addition 2 plus 3 type of scalar addition, meaning that that's something you already know. Okay? So this is what we do quite often. It is a mathematical, how should I say, procedure we use quite often. We define something new by something we already knew. Okay? So although they are same plus sign, completely different meaning. Those are addition of just numbers, and that is addition of matrices. Okay, subtraction. Next one, subtraction. But they're pretty much the same thing, right? Again, for the same size only. And vector subtraction is nothing but the element subtraction. Okay, multiplication, the next one, right? Plus, minus, multiply, and divide. So multiplication. All right. Recall the simplest case. Here, this is a place where I said I haven't defined those yet. So this is a place where I will define. We'll see how it is defined. So those two equations will be written in this form here, right? So what we would like to have is that you're multiplying this one and that one, and this set come back to those two equations, then that is great, don't you think? Because if, well, the result of this multiplication becomes a vector of two elements, 2 by 1 vector, and 2 by 1 vector and 2 by 1 vector is equal to each other if the elements are equal to. So elements are equal to. So if you multiply those two and come up with this expression and that expression, if you define the multiplication to be that will be super good. Because we can interchangeably use those set of equations and this matrix equation. So, should retrieve, that's a good word, retrieve the original equation. All right, let's try this. So we want this multiplication to be this. Okay, the upper side is this one here, lower side is that one here. And if this one is equal to that, then ax plus by has to equal to e, and cx plus dy is equal to f. Okay, so if this is defined by that, super. Okay, so how do we do it? Okay, so the top, the first row, and xy, and if you look at it, and to come up with this expression over here, what we do is we multiply a to x and b to y, and put at the top portion. How about cx and xy? cd and xy. We multiply these two, c to x and d to y. Okay, so this is first row multiplied to the column, and second row multiplied to the column. So, interesting thing is that the matrix product is defined by the multiplication of rows of the first matrix to the columns of the second matrix. So if I generalize this, what we're going to have is that each row of the first matrix is multiplied to each column on the second matrix. Okay, so if I write that one down, this matrix times that matrix here is this matrix here. I don't know why this B matrix is bigger. Maybe I made a mistake in choosing the font size or whatever it is. Where C, say for example, C11, you multiply the first row, C11, you multiply the first row of the first matrix and the first column of the second matrix, then you come up with this one here. So if I choose C11, Ji is equal to 1, J is equal to 1. A1K is the first row, and BKJ is J is equal to 1. That's first column here. Okay, so that's what we do. And where I runs from 1 to N, J runs from 1 to L, and come up with this. So this, from this one here, you can immediately tell the number of elements in a row of the first matrix. That's here. How many of them? And the number of elements in the column of the second matrix, you have to multiply them together. So you have to be able to find the corresponding elements. That means this equals to that and that equals to this. So those two must equal to each other. Okay? So the number of elements in a row in the first matrix and the number of elements in the column of the second matrix, okay, are equal to each other. So what does it say? Number of elements in row, meaning number of columns, right? So this first one here is actually, what happened? This one here is actually number of columns of the first matrix. And here, this one here is actually the number of rows, columns and rows. So the number of columns of the first matrix has to equal to the number of rows of the second matrix. And note of the size. Here, this first one was n by m here, this one here, and this is n by l here, and then the resulting one is n by l. Because I changes from up to l, j changes up to l. Right? So that's how the product is defined. Okay. Vector multiplication. Well, you may ask, well, we know how to multiply matrices. The number of columns and the number of rows has to equal to each other, right? But if you are looking at the vector multiplication, if you want to multiply vectors, wait a minute. Vectors, both of them, there's only one column. So number of rows in the first vector cannot equal to the number of columns, rows, and the number of columns, number of columns in the first vector cannot equal to the number of rows in the second vector, because both of them are, say for example, one of them is AB, the other one you want to multiply is CD. Can you multiply this? No, not really, right? Number of columns is 1, 2 by 1. This one is also 2 by 1. So this and that are not equal to each other. So you cannot do that. But there are several occasions where you want to multiply vectors to a vector of the same dimension, actually. So what we do, there are two ways or two things defined. First one is called the inner product. By directly applying the matrix multiplication, but a little bit different. There's a stick to it. Inner product, this one here, is called the inner product, is defined to be transpose of this times that. So if you transpose this one, the first one, then this becomes A, B, and C, D. So the number of columns 2 and number of rows 2. So those two are equal to each other, so you can multiply. Oh, of course, I haven't done a vector multiplication for the same size. Forgot to tell you that. For the same size only. Once again, when you multiply something, you have to have the same number of elements, right? This product, V1, W1 up to Vn, Wn is possible only when you have same number products. Okay? So same size only. Okay. So this is called the inner product. This is called the inner product. All right. Why we use that? Well, if you learn, well, I guess you have learned inner product and the meaning of that when you have two vectors in two-dimensional space or three-dimensional space, what that inner product represents. And I will talk about that a little later. But right now, let me just look at this product and find out some of the properties properties, I should say. First of all, number of the node on the sides. Since you are transposing the first one here, the first one becomes 1 by n. And the second one is, of course, n by 1. And if you remember the product of two matrices, you are going to come up with 1 by 1, a scalar. So the vectors, you multiply together and you come up with a scalar, just a number. So inner product is the one which reduces two vectors into one single number. Node on the direction. Now, from your high school, the vectors do have directions, right? The two-dimensional vectors, A and B. Of course, A and B, you have directions. You have a direction. Here's A, here's B. That's the vector you have learned. 0. Right? So the vector has direction. But if you compute the inner product of two vectors, this one and say, for example, something like this one here, that's C, and this is D. Okay, you multiply those two vectors, you come up with a scalar. It doesn't have direction. Direction is eliminated. So, is there any use for that? Surprisingly, there are lots of use for that. Okay, so I will talk a lot more about this one a little later in relation to what you have learned in high school. But before that, it is not fair to finish vector multiplication just by talking about this inner product. There's another vector multiplication defined, and you will use in robotics as well. That type 2 is called the cross product. I will talk a bit about cross product in coffee break because that is beyond the scope of this class. Okay? That's something you will learn in linear algebra class. I am not going to talk about that more than introduction of that. Okay, so coffee break. You have two vectors. A vector has not only a length but also directions. That's something you have learned in high school. Okay, both need to be considered when you multiply vectors. Yes, when you multiply vectors, when you multiply numbers, you don't have to worry about the directions because numbers do not have directions. But vectors do have directions, so therefore you have to worry about that. And of course, the size of the vectors. Multiplication of directions. Does it make sense? Multiplication of directions? We approach to this problem from two directions. Aha! That's a pun. All right? 1, get rid of the direction. 2, get out of the plane. What do we mean by that? Okay. Get rid of the direction is the inner product we have done. Okay, so we know what this one is. Get out of the plane, that is the cross product. The cross product is a vector which is perpendicular to the plane which is formed by those two vectors. And we use that when we're talking about I didn't write down, but that cross product vector is very handy when we're talking about the torque vector, blah, blah, blah. That's later. Out of the scope. Too bad. Well, probably it's good for you. So, next time we'll talk more on vectors and matrices, especially the one I promised you, the relationship between the vectors you have learned in high school and the vector I defined here, especially of that importance of that inner product. Okay, thank you.